Okay, so welcome back, my little Lewis dot pros, and today we're going to do more examples of Lewis dot structures. Yay! Right, I know you're so excited. Okay, so we're going to go back and we're going to review the rules of Lewis dot structures again, but I'm going to give you a different structure to draw this time, just to show you there are many differences that can happen, but we're going to follow the same rules each and every time, okay? So here we have NH3, and we want to draw the Lewis dot structure of NH3. So how do we do it? Well, we first do a total valence count, right? So nitrogen and hydrogen. So if I go to nitrogen on the periodic chart, up at the top, there's going to be a 5A. So there's 5 valence for nitrogen. And then at hydrogen, there's a 1 up at the very top. It says 1A on that column. Well, the issue here is that we have 3 of them, so 1 times 3 is 3, and I'm going to take 5 plus 3, and that gives me a total of 8. Do not get this confused with the rule of octet. This has nothing to do with octet. The last example, HCl, just so happened to have 8. This example, NH3, just so happens to have 8. That's just the way that these worked out. It is not the way that it will work out every single time. It is not octet driven here as far as this step is concerned. You're going to see this number can get much larger, but that is more complicated types of examples that we will work ourselves up to. So it just so happens it's been 8 in each case. So here's the total valence count. And the next rule said determine the center, and keep in mind that hydrogen can never be in the center. Okay, so that means hydrogen's here, they can't be in the center, so there's only one choice for my center, and that's nitrogen. So over here to the side, I'm going to write nitrogen, and then I'll just kind of draw these hydrogens around it. I mean, it doesn't have to be perfect. I'll try to make them symmetrical when I can to make them look pretty, but quite honestly, it doesn't really matter how you draw them on a sheet of paper. As long as the steps are correct, that's all that matters to me. So just draw 3 hydrogens around them. I don't care how they look. All right, there's no rhyme or reason right now. Just try to make it even and try to make it pretty. And then the next rule said, once you do this, you then connect everything to the center atom using a line. Okay, so I'll draw the hydrogen to that nitrogen, the hydrogen to that one, and the hydrogen to that one. There you go. And it said that each time you did that, you took away 2 electrons. So there's 2 from here, and there's 2 from there, and there's 2 from there. That gives me a total of 6. So 8 minus 6, I've got 2 electrons that are left that I need to figure out where they go. All right, well, the rule of hydrogen said no more electrons other than 2. It doesn't need any more. Well, 2 is coming from the line. So I can't put the dots there. I can't put the dots on that hydrogen to the left. I can't put the dots to the hydrogen on the right. They're full. They don't need any more. So I've got 2 dots. I only have one other possibility. I keep my fingers crossed to make sure that those dots can go where I think they're going to go, and that's to nitrogen. So if I look at nitrogen in the center, he's going to get 2 from the hydrogen bond above, 2 more from the one to the left, and 2 more to the one on the right. That gives me a total of 6. The name of the game is octet. It needs, ding, 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 2 more, and I just so happen to have 2 more that's left. So I'm going to draw 2 dots onto that nitrogen to show you that that is where they need to go. So there's the Lewis dot structure for ammonia, which is NH3, okay? Nitrogen in the center has 3 bonds and a free pair of electrons. That is what we say. And then the hydrogens around the nitrogen each have 1 bond, and it's perfectly happy with just that 1 bond. That's all that it needs. It doesn't need any more. All right, so let's move on to another example, but we're going to go back to this in just a second, and this other example is going to be water. It's very simple. You've seen it before. You've used it often. How do we do a Lewis dot structure for H2O? Well, we do total valence count, just like we did up above. So I have hydrogen and I have oxygen. Hydrogen has 1 valence because that's the group number at the top, and I have 2 of those in total. Oxygen, it has 6 because it's in group 6A, and there's only 1 of them. So 6 plus 2, it just so happens to be 8 again. Again, do not get accustomed to that number. All right, now I need to determine the center of the molecule. And the center of that molecule, it cannot be hydrogen. So therefore, oxygen is my only choice. And I have 2 hydrogens that I need to draw. And again, I just make it pretty. I'll just draw around it somewhere in some form, in some fashion. I just like to make them look equal. Well, I then need to connect everything that I've just drawn to the center atom. So I need to connect the hydrogen on the left to the oxygen and the hydrogen on the right to the oxygen. Doing that, each line took away 2. So I have 2 from here and I have 2 from there, which is a total of 4. So 8 minus 4 is 4. I have 4 more dots to put onto this structure to represent the sharing of the electrons between these atoms. So where are those 4 going to go? Well, I can't put them near hydrogen. Hydrogen maxes at 2. The one to the left already has 2 from the bond. The one to the right already has 2 from its bond. The only place for me to put them right now is to that oxygen. And I hope that oxygen needs 4 of them because that's what I have in order to assign. Well, the oxygen to the left has 2, to the right has 2, that's 4, and it needs 4 more to get to octet. So, woohoo, right? We did our math the right way, we did our structure the right way. Everything works out kind of the way it's supposed to. So there is the total of 8 dots around oxygen at this point. 2 on top and 2 on bottom, 2 from the bond on the left, and 2 from the bond on the right. So there's 2, 4, 6, 8. Who do we appreciate? Me! Because I just showed you how to do a Lewis dot structure, right? Okay, so this is not the only thing that we can do with these structures. So before I do any more examples of these structures, I want to talk a little bit here about shapes of structures. And this is where VSEPR came into play during general chemistry. So VSEPR stands for Valence, Shell, Electron, Repulsion, Theory. Okay? Valence, Shell, Electron, Repulsion Theory. This is VSEPR. So VSEPR is basically a way that we can look at these structures that we have been drawing, and I'm going to write the HCl on here as well because we did that in the last video, and to identify shapes that these things will take on in a 3-dimensional fashion. Okay, so how do we do this? Well, you're always going to get a chart from me, and you can use this chart every single time when you need to, and the chart will look something like this. So how do we read the chart? That's the question. There's a lot of information on here, right? I mean, there's tons of stuff. Well, I'm going to make it easy for you. This total domain over here to the left, you can actually cross that out. I don't really use this column at all in organic, and you probably won't either. So just ignore that that's even there. The next one, this generic formula, well, you're going to cross this one out as well because I never look at it, and you probably will never look at it either once I tell you how to read this chart the proper way. The picture column. The picture column gives you an idea of the types of structure that this thing will take on. And it kind of draws onto a sheet of paper electron orbits, where they're located, bonding atoms, and so forth. I actually don't use this column either. I mean, some people use it as a point of reference just to kind of compare what they have drawn to that column. And if you're one of those people, then great, good for you. But I never really look at that at all. The bonded atoms and the lone pair atoms, though, I do look at. So we're going to keep those columns at least. The next one is the molecular shape. And the molecular shape is going to tell you what shape this structure takes on. So that's the whole purpose of using the chart. So we're going to keep that column. The next one is electron geometry. So there is a choice here, and the choice is, do you want to include the electrons or do you want to talk about the shape not including the electrons. I'll show you which one that we are going to be using when we do our first one. The example over here to the side, I don't really use that column. I mean, great. It gives you an idea, maybe a point of reference, but I actually don't need it, and I don't use that at all. And then the hybridization here, it says S and SP and SP2 and SP3. This stuff is things that will happen later on in actually this lecture module. So this is going to be new material for you mainly, and we're going to cross that out for now. We're not going to look at it at all. And then you're also going to see over here to the right-hand side things that we call bond angles. And bond angles is something that they like to talk about. So we are going to mention that a little bit, but quite honestly, other than just looking at bond angles for those types of questions, we will never use this column either. So I'm going to actually mark this out now as well. And we'll come back and we'll talk about this at a later video at a later time. So it looks like I've taken this chart and I've just whittled it down to really a couple of columns that are here in the center. Okay, so how do I read this? Well, I'm going to go back to the structure that we've drawn, and I'm going to do number 1. And this first one was HCl. So what if someone said, what is the shape of the HCl molecule? So if I had this chart, it makes it very convenient. Notice here, I didn't have a center. And on this chart, the number of bonded atoms is really talking about the center, okay? And the number of lone pairs, it's really talking about the center. That's what we were talking about. Okay, well, we don't really have a center here. There's only 2 things that are here. Therefore, there's only one way that these 2 points can be connected, and that's through a line, folks. That's it. No more than that. So anytime you have 2 atoms that are connected together with one bond, like this one, there's only one possible shape that this thing can be. Any 2 lines make a point, or any 2 points make a line. And this is a linear shape, okay? Think of a cigar, think of a pen, think of a pencil. That's the shape of this molecule. That's how it would look like in a 3-dimensional environment. And it is 3-dimensional, so that is the shape that it does take on. All right, so let's look at number 2. And what if they said, what is the structure or the shape of the water molecule? Well, I've just drawn the structure. There it is. Now I need the shape. All right, so the way that we'll read the chart, this bonded atom, how many things are bonded to the center? All right, so I'm going to go back and take a look at the structure. Here's the center O. There's a hydrogen to the left and a hydrogen to the right. There's 2 things that are attached to the center. So I'm going to be looking for the number 2. All right. This number of lone pairs, this is also in reference to the center. So I'm going to look at the structure and I see a lone pair that's there and a lone pair that is right there. So there's 2 atoms bonded and there's 2 pairs of electrons bonded. So my columns need to say 2 and 2. So here's 2 and 0. That's not it. And as I go down, there's 2 and 1. That's not it. And then as I go down, here is 2 and 2. Right there we are. 2 things bonded to the center. 2 pairs of electrons on the center. So therefore, this thing is a bent shape. All right, so bent shape means that it's going to look like this. And I'm just going to clean that structure up. And I'm going to show that bent environment a little bit more exaggerated. So if you give me this structure up here on the top, you are correct. That is what it looks like. If you want to be more representative of it, though, then you would want to take that molecule and you want to bend it down a little bit. And if you look at the way that they've done this example for you, this example shows you right here, let me erase those lines, that you do get a bent type of environment there with 2 pairs of electrons that are basically right here. So this is the shape that we are after. We are going to call this a bent molecule. Now this is not including the electrons, all right? And that's really the one that we're going to be after here. This electron geometry, this is another shape if we include those electron pairs, but we are not going to be after those in this class. We're not going to be after those, especially in this very first chapter. So I'm going to tell you to cross that out as well. But that is a shape that is assigned to the structure if you want to include the two pairs of electrons that's on this particular type of molecule. That would be called a tetrahedral. But we're only going to be after molecular shape. That is what we want. That's what we're after. That's what these questions will be asking about. So knock off that other column. You don't need it. But if they do want to talk about electron geometry, then that's the shape name that you're going to be after. All right? So let's look at our other one. This one we know now is a bent molecule. Hydrochloric acid is a linear molecule, or hydrogen chloride. All right, now let's take a look at this one up here at the top, this NH3. NH3 has three things bonded to the center, and it has one pair of electrons on the center. So on that table, I'm going to be looking for a 3 and a 1. So as I scroll down, 1, 2, 1, 3, but that one's a 0, so that's not it. And then as I keep going, 2, 1, 4, 3, and then there's a 1, so there's my match. 3 things bonded to the center, 1 thing as far as pairs of electrons go to the center. So this shape is called a trigonal pyramid. All right, so a trigonal pyramid would be the shape of this structure in a three-dimensional fashion. If I take a look at their example and I take a look at how they've drawn it, if you notice, it looks like a tripod to me that you would put a camera on. So this tripod has 3 legs at the bottom that hold this whole thing up. And then on the top is the platform that you would connect your camera to. So this thing looks like a tripod. So the term that we use for that is called trigonal pyramid, or trigonal pyramidal. Sometimes you would see that in a table as well. Okay, so that's how we use this, what we call Vesper chart, in order to assign 3D structures to a molecule. And this is something that you learned in general chemistry, at least I hope it was presented. This is something that you probably spent a whole chapter on, at least I hope that you did, drawing structures, assigning shapes, talking about Vesper models. That is what all of this boiled down to. Polarity, we can't forget about polarity, right? So the way that I want to show this is that this molecule is polar. Okay, that bond shows me some polarity right there. Hydrogen and nitrogen, this is a polar bond, and it points toward the negative sides. So there's polarity on the individual bonds right there. And then on my water molecule down here at the bottom, if I want to show it on the individual bonds, I'm going to show it, I'll do it here in the bent shape. One pointed up like this, and one pointed up like that. We can also talk about the overall polarity of the molecule. What I've done here is that I've just assigned polarity or dipoles on the actual bond between the two atoms. But we can also talk about the overall polarity of the molecule. Well, for number 1, that is the overall polarity. There's only one bond represented. That one bond got polarity assigned to it, and we call a done deal. Number 2, well, this one is a little bit different because there's more than one bond. Each one of these, look at this, points in the same direction, right? So the overall polarity here is a yes. We do have overall polarity, and it points toward the center. And if you look at the way that I've drawn this, this points slightly up and this points slightly up. So I can kind of show the whole thing as an overall polarity that basically goes up. So I can do a molecule polarity, and I can also do an individual bond polarity. What you're going to find out is that all bent molecules, they are polar. No matter what they are going to be polar. The reason is because of their shape. Look, you get this electron cluster that's going to be right here. that electron cluster is in the center atom, and it's an unequal sharing of the entire molecule, so that molecule will be polar because of that reason. There's no electron pairs on the outskirts to cancel anything out. The trigonal pyramid, it's also going to be polar almost every single time. I mean, if you take a look here, everything points toward the nitrogen. So I can somewhat draw a polarity that looks like this overall. It is a polar molecule because it has polar bonds on the inside, and those polar bonds do not cancel each other out. So almost all trigonal pyramid are going to be polar as well, as far as the molecule goes. Again, you'll see that this electron pair is on the center. There's no electron pairs on the outskirts to cancel it out. This is an unequal sharing of electrons, so therefore this thing is polar every single time we get this shape. So just kind of a tidbit of information. We'll start taking a look at this more and more later on, but this gives you a couple of examples of drawing Lewis dot structures. So in the next video, we'll do a few more, and then we'll move on to the next lecture topic. But again, I want to give you enough of these examples so that you'll feel comfortable with them. And we'll pick up some more when we come back.